Imagine walking into a grocery store 20 years from now. The shelves are half empty, prices have skyrocketed, and fresh produce is hard to find. What happened? The answer isn't a simple one. It's the result of a growing population, labor shortages, and a food production system that's struggling to keep up. Right now, we have more people on Earth than ever before, over 8 billion. And by 2050, that number will reach nearly 10 billion. But our ability to produce food hasn't grown at the same pace. The amount of farmland isn't increasing, and farmers are leaving the industry faster than new ones can replace them. The challenge is clear. If we don't find a way to produce food more efficiently, shortages will become inevitable. But how did we get here? And why is this problem more urgent than ever? Farming has always been the backbone of human civilization, but today it's at a breaking point. Let's start with labor. Farms around the world are facing severe workforce shortages. Agriculture is physically demanding, wages are low, and younger generations are less interested in pursuing it as a career. As a result, crops are going unharvested, food production is slowing, and costs are rising for everyone. But that's only part of the problem. Climate change is making growing conditions unpredictable. Droughts, heat waves, and flooding are threatening harvests. In some regions, the growing season is shifting, while in others, entire crops are failing. And finally, we have a land issue. The land available for farming isn't increasing, and in many cases, it's shrinking due to urbanization and soil degradation. We need to grow more food, but we're running out of space to do it. Taken together, these challenges create the perfect storm, one that could lead to a future where food shortages are common and prices are unaffordable. We need solutions, and we need them now. Even with automation, farmers still rely on human labor for delicate tasks like fruit picking and vegetable harvesting. Vertical farming is costly and impractical for staple crops like wheat and rice, and while genetically modified crops help, they don't solve the deeper issue of labor shortages or the declining amount of farmland. We need a solution that is scalable, adaptable, and capable of working alongside traditional farming. That's where robotics comes in. What if we could deploy autonomous robots to work in the fields? Machines that can plant, monitor, and harvest crops with precision. Unlike human labor, robots don't tire, don't require wages, and can work around the clock. They can be programmed to identify ripeness, navigate complex terrain, and handle delicate produce without damage. Robotics has the potential to revolutionize farming in ways that traditional mechanization never could. Instead of simply replacing labor, robots can enhance it, allowing farms to operate more efficiently. But there's still a long way to go before robots become a widespread solution in agriculture, particularly in space-constrained environments like high tunnels and greenhouses. Many existing systems rely on large, high-resolution depth cameras mounted near the end effector for precise perception. While effective in open fields, these systems become impractical in confined spaces where bulky hardware limits maneuverability and increases the risk of collisions. Another challenge is target localization and grasping accuracy. Many systems struggle with small fruit detection, especially when relying solely on a depth sensor that are noisy in cluttered agricultural settings. Planning and real-time adjustments are challenging with small onboard computers, but are crucial for applications, especially in dynamic, cluttered environments. Without precise target refinement, errors accumulate, increasing failure rates. To address these challenges, our research introduces a co-designed perception framework that optimizes both global target detection and real-time local refinement, allowing for precise, adaptable harvesting without the limitations of traditional depth camera systems. Our research introduces a framework designed to address these constraints while maintaining precision and efficiency. Our system leverages a global RGBD camera at the manipulator base for initial target detection and a wireless eye-in-hand RGB camera at the tip for precise real-time visual servoing. This dual camera setup enables accurate localization of small fruits while reducing hardware bulk at the end effector. The global depth camera scans the surrounding environments looking for ripe fruit to pick. Once a fruit is detected, the robot arm moves to an initial position in preparation to grasp the fruit. Then, our visual servoing method iteratively centers and approaches the fruit. When the fruit is detected between the grippers, the pneumatic actuators enable the grasping and the arm plucks the fruit off. In cluttered environments, a depth camera at the end effector can cause occlusions, preventing efficient and robust grasping of the target fruit. We solve this problem using a co-located camera with our visual servoing method. In real-world testing in high tunnels, our system successfully reached 85.0% of cherry tomato fruits in an average of 10.98 seconds. Our findings show that a compact, co-designed perception framework can improve fruit localization and harvesting efficiency without the need for large, high-resolution depth cameras. Here is a demonstration of our system working in the high tunnels here at the university. This research is more than just an academic exercise. It has real-world implications. If robots can successfully integrate into farms, we can address labor shortages, reduce waste, and improve efficiency at every stage of food production. With scalable robotic solutions, we have the opportunity to transform agriculture, not just for large-scale industrial farms, but for smaller farms that need technological support the most. This is how we ensure that in 2050, when we walk into a grocery store, the shelves aren't empty. Instead, we see an abundance of fresh, affordable food powered by intelligent automation. But this is just the beginning. Future research must focus on improving robotic dexterity, making systems more affordable, and integrating AI for real-time decision-making. Collaboration between researchers, engineers, and farmers will be crucial in refining these technologies and bringing them to scale. The road ahead is long, but the potential impact is enormous. The future of farming will not be built by tradition alone. It will be built through innovation. We would like to thank our collaborators, funding sources, and everyone who has contributed to this research. The challenge of feeding a growing world is one we all share, and through continued innovation, we can rise to meet it. Thank you for watching.